This is the 27th AIP Open Seminar Talks by Causal Inference team. I'm Shohei Shimizu, the PI of the Causal Inference team. Okay, so before starting the seminar, here are some important notices about this seminar. So reproduction is prohibited. And the second, reproducing all or any part of the contents is prohibited without the author's permission. And the third, this seminar will be recorded and the video will be available on the Recon AIP website later. And finally, if you have any questions and comments, please scroll to the bottom of the page and click the Q&A tab. You can put questions and comments in the box. If we get many questions, then we might not be able to answer all the questions. But yeah, I hope you can give many feedbacks to us. So let's start. So the Causal Inference team consists of methodologists and also scientists, and we aim to develop data-driven statistical methods for learning causal structures, which is called Causal Discovery from theoretical and philosophical perspectives. And we also aim to contribute to the solution of the problems in basic sciences and applied sciences. Not only to the methodology of causal inference or causal discovery, we'd like to collaborate with people in basic sciences and applied sciences, and also in people in industries. And in fact, we are collaborating with some industrial partners, Toshiba and Fujitsu in Riken Center. The members are, we have one postdoctoral researchers and 4 visiting scientists, and we have some collaborators, interns. We accepted some interns in our team, and Yana was the past intern of our team, and she will talk about his work. Sorry, not her work in this seminar. So statistical causal discovery is a methodology to infer causal graphs based on data. So we combine assumptions, background knowledge, and data to infer the causal graph, the underlying causal graph. So for instance, we make some assumptions on the causal relationships, linear or nonlinear, or we have unobserved common causes or not. And which also we choose the relation is acyclic or cyclic. And then after we make some assumptions on the data generating process, the causal relationships, then we combine the assumptions with the data we collect, and then we infer which causal graph is plausible based on the data and the assumptions. So we want to estimate this kind of causal graph that represents the causal structure of the variables, like this. So this kind of methodology has been applied in many areas. So for instance, epidemiology or economics and neuroscience and chemistry. We are also collaborating with people in these 8 years and tried to contribute to such basic sciences and applied sciences. So the reason why we are working on causal discovery is causal graphs are the key to statistical causal inference. So for instance, one of the main goals in statistical causal inference is to estimate intervention effects and also counterfactuals. When we want to estimate intervention effects or counterfactuals, we need causal graphs, the causal structure of variables we have. So otherwise, we cannot estimate the intervention effects or counterfactuals. And also, we need causal graphs to build counterfactually fair machine learning models. So many people are working on fair machine learning models, but some people are also more people are using statistical causal inference methods to build counterfactually fair machine learning models. Also, in this case, we need causal graphs to build those fair machine learning models. And also, causal graphs are necessary to understand the prediction mechanism of machine learning models. And also, they are useful to build explainable machine learning models. More people are trying to use causal inference methods to build those advanced machine learning models. So what I'm trying to say is causal inference. Many people are interested in, many machine learning people and other people are interested in statistical causal inference, but to enjoy the nice things of statistical causal inference, we need causal structures, causal graphs of the variables we have. So causal discovery is sort of fundamental topic of statistical causal inference, and also maybe intersection of causal inference and machine learning. So we have 3 talks for today. First, Takashi Maeda-san will talk about causal discovery in the presence of unobserved variables, and recently accepted in UAI. And also, Yana will talk about causal discovery with multi-domain link-unfolded factors in accepted in EJICAI this year. And the first 2 talks are about the methodology of causal discovery. And the third, finally, June, Otsuka-san will talk about more general things, causal modeling from a philosophical perspective. So, so I hope you enjoy the 3 talks. If you have any questions and comments, please scroll to the bottom of the page and click the Q&A tab. You can put comment on or questions in the box. Maybe we cannot answer all the questions, but we are very much welcoming your questions and feedbacks. Maeda-san, are you ready?
So hello everyone. My name is Takashi Nicholas Maeda. I'm a postdoctoral researcher at Riken. So my talk is about causal discovery in the presence of unobserved variables. In this talk, I would like to talk about 2 of my recent papers. The first is an extension of a causal discovery method called lingam to incorporate unobserved variables. The latter one is about causal discovery method when the causal relationship is nonlinear and unobserved variables are present. The second paper is not available yet, so we will make a preprint paper available soon. The purpose of causal discovery is to reveal the structure of causal relationships among variables using only observational data. Most causal discovery methods make assumptions about the data generation process. By assuming a model for the data generation process, causal discovery methods are derived from the assumptions. Some causal discovery methods assume causal relationships in the form of a function. The linear model was proposed by Dr. Shimizu. In this equation, xi and xj denote observed variables. bj is a constant. ei is an external effect on xi, and pai is the set of the direct causes of xi. Pa stands for parents. In this field, direct causes are often called parents. In nonlinear cases and post-nonlinear cases, functions fi and gi are nonlinear. All those models assume that there is no unobserved variables. If there are only two observed variables, the variables can be formulated as the equations shown in this slide. It is proved that if the external effects Ex and Ey are non-Gaussian, the direction of causality between X and Y is identifiable. So let's look at an example. Assume that X and Y are formulated as the equations in this slide, and where Ex and Ey are uniform. The scatter plot in the middle is a graph of X and the residuals of Y regressed to X. As shown in this graph, the residual is independent of X. The scatter plot in the right is the graph of Y and the residual of X regressed to Y. This graph shows that the residual is dependent of Y. So the causal direction can be identified by regression and testing the independence between the residual and the explanatory variable. The bivariate nonlinear case can be formulated as the equation in this slide. Even if the external effects Ex and Ey are Gaussian, the causal direction can be estimated correctly if function f is nonlinear. The three graphs above, when the causal function is linear and the external effect is Gaussian. And the three graphs below, when the causal function is nonlinear and the external effect is Gaussian. In these graphs, only the probability distribution of X condition to Y depends on Y. When it is nonlinear, the residual of Y regressed to X is independent of X. But the residual of X regressed to Y depends on Y. So as in the case of lingam, the causal direction can be identified by regression and independence testing. So next, I will talk about the study on the linear cases to incorporate unobserved variables. The model can be formulated as the equation in this slide. Fk denotes an unobserved variable. Lambda ik is a constant. And xm and xn have the same unobserved common causes when there exists a case satisfying that lambda mk is not equal to 0 and lambda nk is not equal to 0. In this study, we proposed a method to infer causal structures in the presence of latent confounders. The left graph shows that the data generation process where the squares indicate unobserved variables and the circles indicate observed variables. The proposed method aims at inferring a causal graph as shown in the right. In this graph, the bidirected edges indicate the existence of unobserved common causes, and the directed edges indicate the direct causal relationships. We call our proposed method the Repeated Causal Discovery, RCD. It takes 3 steps. First, it identifies the ancestors' direct or indirect causes of each observed variable. Second, it extracts the parents' direct causes of each observed variable. Finally, it identifies variable pairs that are affected by the same latent confounders. In the first step, RCD prepares a set of variables mi for each xi. Mi is initialized to an empty set, and it collects the ancestors of xi. In this step, the following process is repeated until each mi no longer changes. RCD calculates the residual of xi and xj regress to the intersection of mi and mj for each variable pair xi and xj. We let yi and yj denote the residuals of xi and xj. If yi and yj are not correlated, then there is no causal relationships between xi and xj. If the residual of yi regressed on yj is independent of yj, then xj is added to mi. In the second step, RCD extracts the parents of each observed variables. RCD prepares a set of observed variables, pi, for each xi, and pi is initialized to an empty set. For each xj in mi, if the residual of xj regress to intersection of mi and mj is correlated with the residual of xi regressed on the set of difference of mi and xi, then xj is added to pi. In the third step, RCD identifies the variable pairs having the same unobserved causes. We prepare a set of observed variables, ci, for each xi that collects the variables that have the same latent confounders with xi. If the residuals of xi and xj regress to mi and mj respectively are correlated, the xj and xi are added to cy and cj respectively. Finally, if xj is included in pi, a directed edge is drawn from xj to xi. If xj is included in ci, a bidirected edge connects xi and xj. Next, I will talk about the extension of nonlinear cases to incorporate unobserved variables. We first show the difference between linear and nonlinear cases of how unobserved variables affect the identifiability of causal directions when there is an unobserved variable. Assume that x1 has an indirect causal effect on x3 mediated through unobserved variable y2. In linear cases, the residual obtained by the regression of x3 on xy is independent of x1. On the other hand, the residual obtained by the regression of x3 on x1 cannot be independent of x1. When the causal functions are nonlinear, x3 can be formulated as the equations in this slide. Then there is no function gx1 that cancels out x1 from x3. So the residual of x3 regressed to x1 cannot be independent. Therefore, it is impossible to determine whether x1 or x3 is the cause of the other. By generalizing this, the causal relationships between x1 and x2 cannot be identified in the cases shown in this slide. The above graph shows x1 is an indirect cause of x2, and the effect of x1 is mediated through the direct unobserved cause of x2. We call this type of path unobserved causal path, UCP. The below graph shows that x1 and x2 have a common ancestor. And the effects of the common ancestor are mediated through the direct unobserved causes of x1 and x2. Because it is impossible to remove the effects of the common ancestor from x1 and x2 by regression, the causal relationship between x1 and x2 cannot be identified by regression and independence testing. So we proposed a causal discovery method called causal additive models with unobserved variables, CAM-UV. The model assumes that the causal functions take the form of generalized additive models. That is, each observed variable consists of the sum of the nonlinear effects of observed causes and unobserved causes, and the external effect. In this equation, yk denotes an unobserved variable. The goal of our proposed method is to infer the causal directions of all the variable pairs that do not have a UCP or UBP. In addition, the method indicates variable pairs having a UCP or UBP by a dashed edge. So in this graph, x2 and x3 have UBP, and x4 and x9 have unobserved causal path. So in a similar way to RCD, CAM-UV takes 3 steps. First, it identifies the non-descendants of each observed variable. Second, it extracts the parents of each observed variables. Finally, it identifies variable pairs having a UCP or UBP. In this first step, CAM-UV prepares set PI for each xi, which is initialized to an empty set. It collects the non-descendants of xi. Non-descendants are the variables that are not ancestors of xi. So the proposed method takes a repeated procedure. It finds a set K satisfying the equation in this slide. where G1 and G2 are functions that take the form of generalized additive models. Then each variable k in K is added to Pi. In the second step, Xj in Pi is removed from Pi if the equation in this slide holds. We conclude that the remaining variables in Pi is the parents of Xi. Finally, the method identifies variable pairs having a UCP or UBP. Set C collects variable pairs having UCP or UBP. If the residuals of Xi and Xj regress to Pi and Pj, respectively, are correlated, the variable pair Xj and Xi is added to C. So finally, if Xj is included in P, a directed edge is drawn from Xj to Xi. If the variable pair Xi and Xj is included in C, a dashed edge connects Xi and Xj. So this is a summary of today's talk. We propose the methods to infer causal relationships between observed variables in the presence of unobserved variables. In linear cases, the causal relationship between two observed variables can be identified if there is no unobserved common cause. In nonlinear cases, the causal relationship between two observed variables can be identified if there is no unobserved common causal path, UCP, or unobserved backdoor path, UBP. So that's all. Maybe I talked so fast, so we have much time to answer questions. The first question is that in the first work, did you study the identifiability of confounders? This is a linear case that do not have latent confounder. So if there is a latent confounder of X and Y, so then the residual of X regress to Y is dependent of Y, and the residual of Y regress to X is dependent of X. So in that way, it is possible to prove that it is possible to identify the confounders. The next question is, in general cases in causal inference, so is it possible to think that the residual and the explanatory variable are independent? Sorry. Okay. If the residual and the explanatory variable are independent, is it possible to conclude that there is a causal relationship between the two variables? Based on our assumption on the data generation process, first, if there is a causal relationship, the two variables must have be correlated. Then if the residual and the explanatory variable is dependent, then we consider that there is a causal relationship. There is a question that in the nonlinear case, I was wondering which regression method you used. So because our assumption on the causal function limits the causal function to generalized additive models. So we used GAM regression. So, but I think it is possible to use other type of nonlinear regression, such as Gaussian process regression. But yeah, I use the gamma regression. Other questions? In nonlinear cases, are the functions do you assume a specific form of a function on F1 and F2? And we do not have any assumption on the function F1 and F2. Oh, so all the functions can be any form. So other question, if when testing the independence, the hypothesis of the when the hypothesis of the independence, so do you conclude that the variables are independent when the hypothesis of independence is denied? So we use the p-values of h-sig. H-sig is used for so measuring the independence of nonlinear relationships. So and so both of our methods requires hyperparameters. So the alpha level. So if the p-value of h-sig is greater than the alpha level, we conclude that the variables are independent, mutually independent.
前田さん、
はい。
we are running out of time, so
Okay.
can you
So
answer the remaining questions later? On
I think I have already answered all the questions.
Okay.
Okay. Yeah. So thank you very much for listening.
The video will be available on the Recon website. I put the link to the video list on the chat. So if you are interested in, please visit the website. Okay, the next talk is the next speaker is Yana.
Good afternoon, everyone. I am Yang Zhen, and you can call me Yana. I am from Guangdong University of Technology in China, and today I will talk about one work. Its name is Causal Discovery with Multi-Domain Lingam for Latent Factors. Just as Professor Shimizu introduced, this work was accepted by EGCAIF this year, and it was done when I worked with Professor Shimizu last year in Riken in Japan. So today it is my great honor to share this work with all of you here. And now I will begin to share. My talk will begin with the following sections. Firstly, I will give you some introductions about this work, and then I will tell you what is the problem definition is, and then I will share the model identification. Later, I will talk about how to estimate this model. And finally, I will show you some of our experimental results about this work. Thanks for the Professor Shimizu. He had told us that causal discovery's definition. So here I would happy to say that causal discovery is very important, and also there are some famous people who has shared their feelings about the causality. There is a philosopher named Democritus. He once said that I would rather discover a single cause than become a king of the Persians. And the Judy Poe also said, maybe last year, he said that to build truly intelligent machines, teach them cause and effect. He has also shared that the causal discovery is one of the 7 important tools to go to the strongly intelligent society. So I would like to say that causal discovery is very important and has been rapidly developed over the past decades. And what is the causal discovery? Professor Shimizu and Maeda-san has told us that causal discovery is when we have some observed data and we give it some assumption in such as the functional forms or etc. We use some causal discovery methods to infer the causal graphs between the observed variables. This is the causal discovery's definition. Actually, we usually think that causal discovery is based on the causal structure between the observed variables. But this is not always the case because in many real-world applications, some causal relationships will be embedded in latent variables. For example, sorry, I think I should give you the definition of variables here. The latent variables, or we say latent factors, are those variables that cannot be directly measured. Maeda-san has also shared his work about the latent variables. He tried to uncover the causal structure in the presence of latent variables. But here, I would like to say that our work here is to uncover the causal relations between latent variables. For example, in the field of psychology, and we have some unmeasured variables such as stress, coping, or depression. These variables cannot be directly measured. So in this case, how can we uncover the structure between these unmeasured variables? The answer is that we can make use of the measured variables. Please look at this figure. The unmeasured variable stress has some measured variables S1 to S5, and also the depression and the coping latent variables also they have some measured variables. So by making use of these measured and observed variables, we would like to infer a causal graph between these 3 latent variables. So this is our main focus of this work. Now I would like to share some works about the causal discovery for latent factors. There exist some methods to discover the causal structure between latent factors. Also, we can say latent variables. These methods can be fallen into 2 categories. The first category is the covariance-based methods. These methods mainly use the covariance information of the data to find the causal structure between latent factors. But they have one limitation, that is they may output some structures up to the Markov equivalence class for latent factors, and that is their conditional independence are identical. They cannot output a unique causal structure for latent factors, and this is their limitation. So to address this indistinguishable problem, Professor Shimizu firstly makes use of the non-Gaussianity of the data to try to output a unique causal structure between the latent factors. Professor Shimizu, etc., they tried to conform the problem into the noisy independent component analysis problem, and they used some NICA methods to estimate the structure. And their method is based on the lingam. Besides, Professor Cai, etc., in 2019, they also proposed a constraint called Triad Constraints. This constraint is based on the conditional independence. It can be used to find the number of latent factors and also their causal structure for latent factors. But these two kinds of work, they have also one restrictions. They both focused on the single domain data. So we will have one problem that how can we handle the multiple domain data in causal discovery? As we may know that the multiple domain data are very, very common in real world. Multiple domain data are the multiple domain data. They may have some distinct distributions, or they may have different causal effects. That is, they may be originated from different domains. For example, in biology, a particular disease is measured by equipment. So when we use this different equipment to collect the data, and in this case, the data may be multiple domain. So now I would like to say that existing methods to handle the multiple domain for causal discovery are flourishing. There are many works on this for the causal, but to uncover the causal structure among the latent factors, given the multiple domain data. To the best of our knowledge, there is no literature that have done this work. So we would like to address this problem. That is, how can we perform causal discovery from multiple domain data to discover the causal structure among the latent factors? Now I will give you the detailed problem definition. Firstly, suppose we have m domains. The lowercase m represents the m's domain in the data. And here, fm is generated by a DAG plus a noise epsilon, and x is also linearly generated by f plus a Gaussian distributed error E. So when we have these two equations, we may have two problems. The first problem is we have multiple domain data. So how can we integrate this multiple domain data effectively? To solve this first question, we use a simple coding representation method. This method is referred to the Shimodala paper. The simple coding representation method means that for one specific observation, only the PM dimensions come from the original domain, while the other P minus PM dimensions are padded with zeros. Please see this the equation below. We can know that this newly augmented data is obtained with its original data for only PM dimensions, and the other dimensions are all zeros. So for simplicity, we use a bar to express this all augmented data. Using this simple coding representation method, we would like to establish the model further. Please see the figure on the right. Yeah, so we have addressed the first problem. Now we have the second problem here. We know that there are many latent factors Fm in different domains, but how can we know that which latent factors in different domains Fm is represented by the same latent factors of interest? So to address this problem, we introduce another latent factor called latent factors of interest. It is represented by a notation F tilde. And we also assume that F bar, the augmented latent factors F bar, and the latent factors of interest F tilde are having some linear relationships. That is this equation. So here it's our whole model's definition. To be concluded, our model has 4 assumptions. The first assumption, A1, is that we assume that the latent factors from the M's domain Fm are generated linearly from a directed acyclic graph, and also they have some non-Gaussian distributed external variables. And then the second assumption is the observed variables domain are generated linearly from the latent factors in the M's domain Fm, and plus the Gaussian distributed errors Em. And then for the latent factors Fi, we will assume that each Fi has at least 2 pure measurement variables. The pure measurement variables are those variables which have only one single latent factor parent. As shown in this figure, every Fi all have two pure measurement variables. The fourth assumption, A4, is that each augmented latent factors Fi bar in the M's domain is linearly generated by only one latent factors of interest F tilde, and each F tilde generates at least one latent in the augmented latent factors F bar. We made this false assumption according to in order to make the model's identification. And this is the model's definition. And so, given this model, we would like to say that our goals is we have two goals. The first one is for the multiple domain data, we would like to estimate the causal structure between the latent factors of interest, the F tilde, and also the factor loading matrix G here. And we also called this model as MD-Lina model. And the second goal is for the single domain data. If we have some single domain data and we can neglect the false assumption and we can only focus on this pink causal graph. In this case, we want to estimate the causal structure between the latent factors and also the factor loading matrix G. And this model is simply abbreviated as Lina model. For some convenience introduction, I would like to say firstly that our model can be regarded as two different models. The first one is the measurement model. The measurement model is relating the structure from the observed variables xm to the latent factors fm. This is called the measurement model, and the structure model is recording the causal relations among the latent factors in the M's domain fm or the latent factors of interest F tilde. So having shared the problem formalization, we would like to give you some model identification results. We proved the model identification from two aspects. The first one is for the single domain data, and the second one is based on the multi-domain data. We can see it is in this lemma 1 that if the single domain data strictly followed our model assumption, then the latent factor matrix G G is identifiable up to permutation and the scaling of columns. Also, the causal effects matrix B is fully identifiable. This lemma 1 is proved mainly by the triad constraints and the identifiability from one of the Professor Shimizu's paper. This paper mainly focus on the same problem. It is the NICA method. And the second identification result is for the multi-domain data. And the result is shown here. If we have some multi-domain data X, and they also strictly followed our MD-Lina model, then also the underlying factor loading matrix G bar includes all of the all of the factor loading metrics in different domains. And this G bar metric is also identifiable up to permutation and the scaling of columns. And also the causal effects metric B tilde is also fully identifiable. This theorem one it's proved mainly based on the lemon one. So when we know that our model is identifiable, and now we want to estimate this model. For the model estimation methods, we mainly propose a two-phase framework. The first phase is the measurement model phase. The second phase is the structural model phase. In the measurement model phase, we have two kinds of methods to estimate the structure. The first one is that we can firstly use the triad constraints to determine the number of latent factors in each domain, and also to yield the structure between the latent factors in the M's domain and the observed variables in the M's domain. Having obtained the structure between the X and the F, and we can simply employ the confirmatory factor analysis, abbreviated as CFA, to estimate the factor loading matrix. This is the first approach, and we can also use some exploratory approach for estimating this measurement model. For example, we can use the exploratory structural equation modeling methods to estimate the factor loading matrix, and it has some fewer restrictions. In our algorithm, we mainly use the first method to estimate the measurement model. When we have the factor loading matrix G bar, we can use this equation to get an estimate of the augmented latent factors F bar. So in the second phase, we want to estimate the structure model. We mainly view this problem as a continuous optimization problem. We introduce the log likelihood functions of Lena model and the MD Lena model respectively. So at first, I will try to introduce the log likelihood function of Lena here, and then I will unify this Lena's log likelihood function into the MD Lena's log likelihood function. The log likelihood function of Lena is based on the joint distribution shown in the first equation. And then we take the logarithm towards this joint distribution, and we can get the log likelihood L with the matrix B and the estimate, the matrix G. Here we can see that this log likelihood function has 3 parts, and C is a constant. Actually, the first part here, it's mainly measuring the non-Gaussianity of the errors E. The errors E is from the observed variables X. And the second part mainly characterizes the independence relationships between the the noise variables from the latent factors F. So our log likelihood function here is here. Then when we have this log likelihood function, we have our objective function. Our objective function is that we want to minimize this f function with the metric b and the estimated metric g, such that this h function equals to 0. The h function with the metric b here is an oscillative constraint. It will constrain that that the causal structure between the latent factors are generated by a DAG, by a directed acyclic graph, by a DAG. And the main objective function f here consists of the log likelihood function and adaptive sparsity regularization and plus another L2 regularization. Lambda 1 and lambda 2 are two regularization parameters. From this objective function, we can simultaneously estimate the causal directions and the causal effects between the latent factors, and it can reduce some computationally complexity. When we have this objective function in our algorithm, we use the quadratic penalty method, namely QPM method, to optimize the metric B. This quadratic penalty function is S. The function S with the metric B equals to the objective function F with the metric B and the estimated metric G plus oscillative constraint function. Here, rho is the regularization parameter. So after we have this quadratic function, we can use some gradient descent method to optimize the metric B. And this is the log likelihood function of the Lena model for single domain data. And now I will show you how to unify this log likelihood function into the multiple domain cases. Here, these two equations show the objective function for our MD Lena model. This objective function is a little bit different from the log likelihood function for the single domain data. This objective function wants to minimize the function f bar with the metric fb2 and the metric g, such that the causal structure between the latent factors of interest f2 is a DAG. So we also have this kind of oscillative constraint. And then the f bar function equals to the f function plus another error function related to the metric h and plus another sparsity regularization with metric h. Here, the f function with the metric b2 and the metric h equals to the following equation. As we can see in this method, it is similar to the Lena model's log likelihood function. The first part is that it also characterizes the non-Gaussianity of the error variables from the observed variables x. And also the second part characterizes the independence of the epsilon. This epsilon means the noise variables of the latent factors of interest f2. So this is the first part in our adjective function. And for the error function with the matrix H, its equation is shown here. It is actually a reconstruction error function, since we assume that the f bar equals to H times f2. So this is actually a reconstruction error function. After some transformation, we can have this kind of result. Here, the matrix PH equals to a matrix with the matrix H. It is a projection matrix onto the column space of the matrix H. So this error function with the matrix H actually characterizes the dependent relationships between the f2 and the f bar, and log likelihood function of MD linear. And then we would like to try to optimize iteratively two matrices. They are the matrix B2 and the matrix H. We mainly use the quadratic penalty methods as well. Firstly, we want to optimize the transformation matrix G, and we find its descent direction of the matrix H to derive its next iteration for a given matrix B2. And then to optimize the matrix B2, we try to find its descent direction to derive the next iteration for a given matrix H. Since the first step here to optimize the matrix H is an unconstrained problem, so we can directly optimize the matrix H. But to optimize the matrix B2, this procedure is a constrained problem. It has it has an oscillatory constraint. So in the second step, we have to update the penalty parameter rho in the quadratic penalty function until this oscillatory constraint is satisfied. The next step is to repeat the following two steps until these two metrics are convergent. When we get the matrix H, we can link the factors from multiple domains with the high weights together to symbolize the same latent factors of interest. It means that with the matrix H, we can know that which latent factors from different domains is represented by the same latent factors of interest. And now in this way, we can address the second problem we have introduced before. So with this matrix H, we can update the matrix B2 so that we can get the final causal structure between the latent factors of interest. So this is the overall estimation procedures Here is our algorithm. That is, in phase one, we estimate the measurement models, and then in second one, we estimate the structure models. Having given our algorithm, we also prove that our algorithm, under some conditions, our algorithm can consistently find the factor loadings matrix G bar and the H, and also we can locally consistently estimate the causal effects matrix B2 up to its stack solution. Now we would like to show you some of our experimental results. Firstly, since there is no existing methods for multiple domain data to discover the causal structure between latent factors, so firstly, we performed some experiments on single domain data and compared our method with the NICA method from Professor Shimizu and the Triad methods from the Professor Tai. And we use different sample size, and we also use different the multicollinearities between the variables. We can see in these figures our methods in most cases can obtain a better performance. What's more, to verify our method's efficacy, we also try to use a comparison which did not conduct the algorithm of which did not conduct the line 6. Sorry, the line 6 is here. For the multiple domain experiments, we compared our methods with the comparison, and this comparison did not update the matrix B2 with regard to the H. And we named this method as MD star. So we can see in these graphs that MD star is our comparison, and with different numbers of domains and the different numbers of latent factors in each domain, we can see that our method with the solid lines are always better than the comparison methods with the dotted lines. Besides, we also perform some experiments on the real-world data. The first one is about the Yahoo stock index data. It has 3 regions. They are Asian, Europe, and the USA region. And each region has its own Yahoo stocks. For example, for the Asian region, it has the Chinese stocks and the Japanese stocks, and for the Europe region, it has some England or French stocks. So using these stocks as the measurement variables, we try to discover the causal relationships between these 3 regions. And we can see that our method A can find a better result compared with the comparison. And then the second real-world data is about fMRI hippocampus data. This hippocampus data has 6 brain regions of a person. They are PHC, SUB, SA3, etc. we see this data as a single domain data. So we use the NICA and the triad methods to make a comparison. We can see in these graphs that our methods A can obtain more consistent edges and less erroneous edges. Besides, our methods can also find some interesting results, such as the relationships between the ERC and the CA1. It is supposed to correlate with the memory loss. This is one of the interesting findings that we have discovered. We can see that our methods can obtain a better result. So this is all of our work. Now I will give you a summary of this work. The first one is our work is the first effort to try to investigate the causal structure between the latent factors for multiple domain data. And we also proposed a corresponding MD-Lena model and show its identifiability results. Besides, we proposed an integrated two-phase approach to uniquely estimate the causal structures among the latent factors, including their causal directions and causal effects. Also, we proved its local consistency. That's all. Thank you for your attention.
Any questions and comments? So if anyone has questions, can you write your question in the Q&A box? Yana will answer
Yes,
later
of course.
before the seminar ends. So if
yes,
you have any
okay,
questions,
no problem.
yeah. Okay. So thank you, Yana.
No problem. It's my pleasure.
Thank you.
Thank you. Thank you so
Okay.
much.
The next speaker is Jun Otsuka. Otsuka-san.
Okay, great. Well, thanks. My name is Jun Otsuka, and I want to talk about this title, the causal modeling from a philosophical perspective. As the title suggests, I'm a philosopher by training. So my talk might be a little bit kind of different or maybe unusual for this venue. But well, what I'm going to do is not, I have no concrete algorithm or mathematical theorems or anything to offer. I don't have any of these kinds of things. I just want to discuss kind of perspective or way to see the things. So from a philosophical perspective, but many of you might not be so familiar with what is philosophy. Well, what is philosophy is a big question. It's a kind of difficult to define, but we philosophers have been interested in kind of three kinds of big questions. So these are three branches of philosophy. One is ontology, which asks what are out there, what in the world, what are in the world. And the next is semantics. So we use symbols, language, and words to represent the world. So how do these symbols and language represent the world? That's a semantic question. And the third is epistemological question. How can we know the world? So these are mainly, well, I do not say that these exhaust all philosophical interests, but these are three main questions. Well, they may sound a little bit nebulous to you, but actually, any scientific field, I would say, has its own philosophical assumptions. So in the case of Newton physics, well, it has its own ontology. That is, well, Newton physicists assume that there is an absolute space and time, and also there are particles with mass living in that space. So this is their ontological assumption. And they use for the concept of force, acceleration, and sometimes use mathematical devices such as differential equations to represent the world. This is semantics. And also, of course, they do experiments and measurements to know the world. This is epistemology. So I would say that any scientific field has these kind of basic philosophical assumptions. And so there's statistics. Statistics has its own ontology. For example, well, we assume that there are data, but not just data. We assume that there are events living in the sample space or maybe sigma field, and they have specific probability measure. And if you are interested in causal search, you might further assume that there is a DAG or some kind of causal structure. And also, statisticians use probability, p-values, average treatment effects, and so on to represent the just assumed world. And also, of course, statisticians are concerned with epistemology, how to know, how to estimate the world. Well, maybe that includes the estimation and MLE, Bayesian conditioning, search algorithms, and so on. So statistician or statistics has these kind of philosophical assumptions. What I want to discuss today is these assumptions and especially the ontological assumption underlying causal search. So these are two questions I want to ask today. What ontological assumptions we are making when we do statistical or causal inferences? Are there differences? And in the second part of the talk, if I have time, well, I want to ask whether we can make this assumption precise. So these are two questions I want to tackle in this talk. Okay, let me start with the first question and with a kind of classical problem of induction pointed out by 19th century philosopher, not 19th, sorry, 18th century philosopher David Hume. So he pointed out, well, data do not tell you anything about the future by themselves. So observations are observation, and you want to predict future event, but there's nothing that implies anything about future event in the observation. If we do some kind of prediction or induction, well, we do assume something more than data, and that more is what he called uniformity of nature. Inductive inference must assume that there is certain kind of stable nature, or maybe what we call the world, beyond data. And thanks to this uniformity, we infer the future event from the past events. And the emphasis here is that this is an assumption. This is an assumption. You can never observe the uniformity of nature directly. You can never establish it as a fact. You assume it. That is a basic assumption, Hume claimed. And this uniformity of nature must be familiar to all of you because probability model is such kind of uniformity of nature. So we have past data and we want to predict future data. And we, in the statistics, assume that there is a distribution probability model. And that probability model is a kind of data generating model. So we sample from this distribution and we estimate this distribution. And by doing so, we make prediction for the future data. That is a very kind of basic, well, maybe too simple picture of inferential statistics. But what we want to note here is that this is kind of ontological dualism. Dualism means that you assume that there are two kinds of things. First is data, and data exists. Of course, data must exist, and they are described by sample statistics. But not just that, we also assume the uniformity of nature or the probability model, and this is described by the probability theory. So with these two kind of things, statisticians make inferences. Okay, then the epistemology of that was ontology of statistics, inferential statistics. but statistical inference is concerned epistemology. It's a concerned epistemological question. Then epistemology of statistical inference is the inference to this hidden layer of probability model from data. So we use data to infer the distribution. Well, of course. And that consists of two kinds of tasks. One is to model this probability model with a so-called statistical model, or that might be, for example, assuming certain kind of distribution family, or make regression model, or maybe make neural nets and so on. So these are kind of modeling perspectives. So we model this thing. And the second, of course, is to estimate these assumed models. And this is a kind of giving estimation identification methods. And this includes, well, of course, Bayesian method, MLE, EM algorithm, AIC, batch norm, and also, of course, the Lingam and the other kind of, no, sorry, so not Lingam, but also those statistical algorithms. So this, from the philosophical perspective, is a kind of ontology and epistemology of statistical inferences. And now I want to ask, okay, well, but what about causal inferences? Well, causal inferences pose a kind of problem. And the question is whether causal inferences are sort of statistical inference. Well, it's a kind of part of statistical inferences. Well, this motivates, for example, multiple regression or structural equation modeling or BaseNet to model causal structures. But I would say that, well, this is a little bit kind of misguided, no offense here, but conceptually speaking, this is a little bit kind of misguided because causality differs from probability in a fundamental respect. Well, in fact sense, I say that, well, they are different semantically. First, because in prediction or statistical inferences are concerned about the actual world. They are kind of inference to the actual world, the actual uniformity of nature realized in this world. But causal claims are about possible or counterfactual worlds. More on this, I will come back later. And ontologically different. Well, because the probability concerns the structure of the world, as I said, that the uniformity of nature, but causality concerns the lawful relationship among or over possible worlds. This, again, I will come back later. So the less of talk, I want to try to specify what I mean by these characteristics of causal modeling from a philosophical perspective. Okay, so then the problem of causality. Well, why causality poses a problem? Because the question about causality is a question about possible outcomes of possible interventions, and intervention breaks the world or the nature. So here we have a past data, and we assume that this past data was generated by a certain distribution. And our goal is to predict the outcome of intervention, but intervention screws up things, messes things up, so it breaks the distribution. But to predict the future outcome, intervention outcome, we have to somehow relate P and P prime. And for that purpose, we need to introduce a kind of higher order uniformity, and that is served by causal models. Okay, so the causal models serve as a kind of higher order uniformity, which generate the probability distribution. And we formulate the operation of intervention within this layer. And the causal inference that was discussed today by Maeda-san and Yana concerns this part, and also Ringham is this part, and intervention calculus or do calculus is the calculation of distribution through this pathway. So this, from a philosophical perspective, is a kind of triadism, and triadism is a kind of unfamiliar word, but it is the assumption that the world consists of three kinds of things. First, data, and second, probability, and the third, causality. So from the philosophical or ontological perspective, the world which is assumed in causal modeling is different from the world which is assumed in probability or statistical inference, because the former is triadism, whereas the latter is dualism. Okay, but well, specifically speaking, what are they? What are these causal models? What are these third guy? I'd claim that this third guy is a kind of nomological or lawful relationship that connects one word to another. What is intervention to begin with? Well, intervention is a mapping from one word to another, right? If you calculate, for example, do x equals small x, this is actually a mapping from the world where x is intact to the world where x is set to small x. And here we mean the world distribution, because I introduced the distribution or uniformity of nature of the world beyond data. So intervention is a mapping from one word / distribution to another / distribution. And the role of causal model is to specify the role of these interworld distribution mappings. So eventually we want to calculate, for example, given a distribution, joint distribution PV, causal calculus, intervention calculus allows you to calculate, for example, the positive intervention distribution over V /2x, so the intervention on X, or you can intervene on Y and calculate the result, or you can intervene on both and calculate the outcome. And so by each intervention, the probability change, the world change. And how do they change? Well, that is specified a causal model. And in this way, the causal model can be thought as kind of determining the dynamics of this intervention calculus. And this intervention calculus, well, mathematician might say that, well, this is a kind of the change in the set of distributions. So this might be a kind of monoid on distribution. So the causal model is a kind of monoid on distribution. Okay, so this is what I mean by the causal model introduced the third layer, and the third layer is this. Now, so the summary for the first part, we have seen in a very short way, the statistical versus causal inferences. We have three kind of things here, and the statistical inference take data as given and try to infer the world or the distribution. And this is a point or region on the set of distribution. This is a target. And in the causal inference, what are given our distribution? It takes distributions as given and try to infer the interworld law. So in this sense, statistical and causal inferences have different ontology and epistemology, different ontology here and different epistemology. So that concludes the first part. Move on to the second question. And this is, I have to say that this is even murkier. This is an ongoing project. And so I don't have a very kind of the fixed result, but the question is whether we can make this assumption, the ontology kind of thing, ontology talk, precise, with the aid of formal theory of categories. And this leads us to a sketch of category theoretic criterion for the equivalence of causal models. And And this is a joint work with Professor Hayato Saigo, mathematician in Nagahama Institute of Bioscience and Technology. So, let's move on to this question now. Well, but why equivalence of causal models, you might wonder. Well, I'm interested in the equivalence of causal model because identity of a thing is determined by the criteria of equivalence. For example, well, I have an identity as a human being, and I think you too. So we are equivalent in the sense of human being, right? So, and we think that the human being exists. So the human being is a kind of ontological category, right? And my identity as human being is determined by this kind of criteria of equivalence. So you and I are same equivalent as human being. But you and I might not be the same as a philosopher. I'm a philosopher, but you might not be a philosopher. So in this respect, in the term of occupation, you and I are not equivalent. So our identities are different. That suggests that the same thing can be described in various ways. And then the question is, when are two descriptions or model the same? That is a question I'm after here. So here, this is a kind of hypothetical example of the effect of diet on heart disease, HD, through the various kinds of cholesterol. So this is low density lipoprotein, it's a good cholesterol, I think. And this is a high density lipoprotein, so this is bad cholesterol. So this model has a kind of final resolution that it distinguishes two types of cholesterol. But here, this is a simpler model, H, and this kind of compress these cholesterol into the one variable, total cholesterol. And the question is, when these two models are the same, are these two models the same? Intuitively speaking, they are kind of modeling the same phenomenon, but they are nevertheless different. So, well, how can we make a precise assumption that these models are targeted at the same thing? To tackle this problem, we resort to a categorical approach to causal modeling proposed by Vert Jacobs et al. In this paper, Causal Inference by String Diagram Surgery. I do not give you the detail here because it's a little bit complicated. But the basic idea is, well, first they translate a causal modeling into the language of categories. Well, why categories? Well, I will explain later. So translating causal model into category. Well, first, the causal model consists of two things. First is a graph, and the second is distribution. And the graph is converted to string diagram first. And then they convert distribution to a functor, or kind of assignment of values and probability to a diagram. We want to see a little bit about these aspects. First, translation of a DAG. So this is the original original causal graph of the diet and the cholesterol and heart disease diagram. And the string diagram consists of strings and boxes. So they look kind of similar, but it is kind of a dual. We translate variables, nodes, to strings, and the arrows to box. And what is the meaning here? Well, we can think this causal diagram of the DAG as representing causal structure by states, that is variables, and their relationship, arrows. But this is one way of looking at the causal structure. Well, we can think, we can look at it in a different way. We can look at it as a combination of mechanisms represented by boxes and messengers among these mechanisms. So first mechanism generate the phenomenon of diet, and this diet is a kind of state, and this will serve as a messenger coming from this mechanism to this second mechanism that generate a low density lipoprotein. And this mechanism then generate low density lipoprotein and feed it into this mechanism that produce heart disease. So this is a view of causal structure according to string diagram. And string diagram has a nice feature. So it has a nice categorical feature. So it gives a category what we call thin G. So, well, we don't have to concern about what are categories. So this is a graph part, and then the probability part. And causal models, what are causal models? Well, causal models are probabilistic assignment of or probabilistic interpretations of string diagram. And that is given by so-called functor from this diagram to another category, stock. This stock is a kind of you can think this as a set of distribution, roughly speaking. This is a category of finite sets and stochastic matrices between these sets. So we have constructed thin G. This represents the causal structure. And we have a probabilistic assignment in stocks. And so these are values of these variables. So we have good diet and poor diet, and we have high density, high good cholesterol and low good cholesterol, and so on. And heart disease no, and heart disease yes. So we translate this functor, assign this variable string to values, and the mechanism, that is a box, to matrices. These matrices are stochastic matrices where each column sums up to 1, and each matrices define the conditional probability of values of, for example, here LDH given diet and so on. So these are kind of familiar things. This is a box. These are conditional probability matrices. So if you assign values to variable and conditional probabilities to each mechanism, well, you get Bayesian networks. You get the causal models. So this is a causal model. This assignment defines a causal model, and this is a functor in the categorical language. Now, we have shown that with graph G, but of course we can do with another graph H. So this is the original graph, and we can convert into a string diagram, and we form the Shin H, and we can assign the probability interpretation by functor B and H, and this is another causal model. And now our question is how they are related. So this is the original graph, original string diagrams, and this functor gives one causal model, B and G. And this is a simpler graph and simpler model, and this gives a simpler string diagram and simpler simple causal model B and H. How they are related, when they are equivalent. First, we think the homomorphism, graph homomorphism from G to H. Here we try to compress these two variables to 1 here. Then this graph homomorphism induce a functor from sin G to sin H. And the question where they are same thing or different is amount to whether there is a systematic transformation from this value to this value so that all the graph commutes here, all the calculation commutes. And this is given by a so-called natural transformation. And the idea is that, well, you can, for example, calculate the probability of LDH of heart disease in the original graph starting from diet, right? Well, you can calculate this and then make it simpler. and kind of compress it to the simpler model. This is one thing, this and this thing. Or you can compress the graph first. You can compress the model first and then calculate in the simpler model and then arrive at the probability of heart disease, this part. When these two calculations end up in the same thing, well, we think that these are the same model. So this is called natural transformation from B and G to B and H. So our proposal is that if there are such natural transformation, this original model B and G and the simpler model B and H model the same thing. This is a proposal. So the proposed definition, let G and H be dogs with a graph homomorphism. The assumption of dog is important here. And sin G and sin H be string diagonal category constructed from G and H. And then we have the induced functor. And also let B and G and B and H be probability models, that is functors from the string diagonal category to stock. Then this gives a probabilistic interpretation that is a causal model of G and H. Then our question is whether they are the same. And we declare that they are the same thing. They model the same causal structure if there is a natural transformation alpha from B and G to B and H, so that this diagram, the above diagram, commutes for all arrows in sin G. In particular, we say that B and G and B and H are the same model if there is a natural equivalence, that is each alpha in the graph here, each alpha here, each alpha here, this one, are permutation matrices. So that is a proposal. This is just a proposal, and there's much to do. Well, what a specific condition for the presence of such a natural transformation and equivalence? We just define the equivalence, but we didn't show, well, under what kind of, which interpretation we have in such natural transformation. We have to work on that. And we limited our search, our discussion here to the finite case. So how can we extend to the infinite or real variables? And also what is the implication to intervention calculus is of course have to be considered. So there are many things to do, but this is just a kind of start, the first try. Okay, so conclusions. In the first part, from a philosophical perspective, I argue that causal models are different in three aspects: semantically, ontologically, and epistemologically. And I discussed more on this in my recent publication in Japanese, here, Tokigako Tetsugakuru. So if you are interested, please take a look. And in the second part, this was a little bit kind of tentative part, and we try to give ontological identity of causal models in terms of natural transformations, but many things remain to be done, and more of this I will give a talk in this month as well, and this should be open to everybody. Acknowledgement, well, thanks to my collaborator Hayato, and also Shohei for being tolerant for philosophers and hosting a philosopher in his team, and Leak and AIP, and also JSPS. Well, many thanks. Okay, so bear with me a little bit. Okay, thanks for the question. What is the difference between treating probability as a monad and treating it as a functor to stock? Well, I think, I'm a very kind of novice to this, but my understanding is that this is a kind of specific example. So if we extend this to continuous case, we get this Jerry monad. I cannot pronounce this, but Jerry monad. So my understanding is that this is a continuous version of the current case. Maybe I may be wrong, but that is my understanding. Anyway, we introduced a kind of monad on stock. So that's basically, I think it's really same to the case of GLA monad. Okay, and the second question, do you claim all the methodology beyond the assumption of the identical distribution are out of range of the statistical inference, or the intervention is fundamentally different from the other methodology beyond the assumption of the identical distribution? Well, the first part, no, I do not claim that because that I understand that you can assume that non-IID distribution in the conventional statistical inferences, but simply because that you can model this non-identically distributed part as a kind of the for example, as a kind of latent Markov structure or something. Yes, I think that the intervention is a little bit different in the sense that it assumes a particular kind of ontology. For example, the assumption may be relevant to the first question or point is non-commutative probability, I think. In the non-commutative quantum probability, you do not assume the fixed probability measure on the set of random variables, in my understanding. But but I think that this is distinguished from the conventional causal search literature. If that answers your question.
So if you have some more questions, you can email Otsuka-san, and then maybe you could discuss more.
Yes, and I'm also on Twitter, so.
Good. You can ask him on Twitter.
Yeah.
Good. That's nice. Okay, so.
Okay, thank you very much.
Thank you. AIP have more seminars, and then the schedule is here, and the next is the next Wednesday. Talks by Pathology Informatics team. This is Japanese language. I hope you can enjoy today's seminar, and you could join these future seminar. So thank you for coming today. See you soon somewhere. Thank you very much.